Welcome to Ghost Likes channel. In today's video, we'll compare Spiral to our favorite language, F#, and compare the features between the two. We'll go over the basic features and the similarities between the two, and show you just how Spiral differs from F# and, in fact, any other language out there. We need to do this because we want to dive in and start doing time lapses, and unless we teach you what Spiral can do, you won't see the benefits it brings to the table. Let's get started. We are going to start things off with the most basic thing, how to create a Spiral project. Just create a new folder. In our case, that will be the tutorial 1. Then inside it, create a package.spyproj file. Don't accidentally name it packages like Ghostlike did just now. If you have it correct, once you start writing inside the package, you should start seeing editor feedback. Spiral has inbuilt editor support for project files, as you can see. To create a module, simply write out its name under the modules field and using the code actions create the file. You can press Ctrl- to open the code actions menu. Once you do that, press the enter a few times. And the VS Code link provider, the part of the editor API under the hood that is responsible for links, should wake up to the fact that the file exists and give you a direct connection to it. Then you just Control-click on it to go into the file. Inside the file, just make a main function and you'll be able to compile it. Note that we've also named the module main, but that doesn't mean anything. At the current time, no functionality is associated with module base names. You only need the main function, and once you are past the type errors, you'll be able to compile it. In our own setup, we just need to press Ctrl F1 to compile it, but that is because we have the keyboard bindings set to that. It is not that way by default. We suggest setting it to that so you don't have to go through the command palette every time. Since we have it set to Ctrl F1, we'll leave it as is. If you go into the editor preferences, openable with the Control- shortcut, and type Spiral into the search bar, you'll be able to see various options for it there. The most important one is the choice of backends. The Python backend we had in the past has been replaced with the Python one. And in addition to that, there are also the F#, reference-counted C, and HLS C++ backends. In this playlist, we'll be focusing on making use of the latter one, but just for this tutorial, we'll briefly go over the F# one as it supports the full range of Spiral's features. Also, the code that gets generated for it is much more readable than for the C++ backend. Let's go over the basic data structures in Spiral next. Tuples, records, and union types are what separate the functional programming languages from the non-enlightened ones, and Spiral has all you'd want from one. We'll do a brief demo of each. Tuples in Spiral are just created using comma-separated expressions. This is very similar to how it is in other fun langs. Records in Spiral are equivalent to F#'s anonymous records, and you don't need to define them ahead of time. Union types, on the other hand, you do, and this is pretty easy. Make a few union cases, and the constructors for them will be exported into the module, allowing you to create them. By rule, types always start with a lowercase in Spiral, as well as regular function and variable names. Union constructors are different and need to always start with a capital letter. The purpose behind this arrangement is to help the bottom-up segment of Spiral destructure the unions. We'll go into Spiral's bottom-up segment later, and it is an advanced topic. For now, let us show you some of the differences between the way how F# and Spiral handle these types. Let's go over the tuples. The main difference between how tuples are handled in Spiral and most other functional languages, F# included, is that they are stack allocated. If we tried to compile them now, we'd get nothing as the partial evaluator has no reason to push them to runtime. But if we instructed it explicitly through this DINE annotation, we should see something come out, though not exactly tuples. Rather, the variables inside of one would be getting tracked individually by the partial evaluator. In order to actually get a tuple, we need to return them from a join point, or an if statement. Here is an example with a join point, and as you can see in the resulting code, a struct tuple is being returned from the function. The C backend works similarly to this. Spiral's partial evaluator monomorphizes the whole program into primitive types, and this allows Spiral to represent its tuples and records as stack-allocated structures in the outputted program. Whereas in .NET, even structs can be heap-allocated due to interaction with generics, in Spiral, These basic data structures are stack allocated 100% of the time. And this guarantee provided by the language is an important reason as to why the language is so efficient and fit for programming GPUs and FPGAs. Other functional languages might be easier to program in or faster to compile, but without the compile time guarantees provided by Spiral, it would literally be impossible to target a device like an FPGA or a GPU. Getting back on track compared to F#, Spiral's tuples also have another difference, namely that they are pairs. On the screen, you can see Ghostlike putting parenthesis around them, and once he hovers over the type, nothing changes. This wouldn't be the case in F#. Since in Spiral the tuples are right-leaning pairs, you can peel them off the same as if they were lists. This is a deliberate design choice to make them more similar to functions. We thought that it would make implementing multi-dimensional arrays easier if they had this kind of behavior. F#'s tuples, on the other hand, have a more array-like representation, and putting parenthesis between them would end up nesting them. Let's play with records a bit next. Records in Spiral are quite similar to how they are in other functional languages, but they do have a lot better syntax. F#'s record syntax is particularly atrocious in our view. In Spiral, you have the punny destructuring similar to JavaScript. Like in F#, you can also update just a single field of a record using the with keyword. By putting a hash sign before the equality, you can use the binding update for a record that takes in a function as an argument and passes the record field into it. In order to use the addition, let us first import the core library. That minus at the end of the package name just means to flatten the package into the enclosing scope, and the bar symbol at the start instructs the compiler to look into the plugin folder instead of the parent of the current project's folder. Going back to records, you can see that the expression we have written out with that plus sign is similar to writing out the lambda explicitly. As Spiral is a functional language, its arguments can be partially applied, and when we do that to a plus function, it applies it, in essence, storing the first argument for later use, returns a function with a single argument, and that is what the record update passes the record field into it. In addition to the with keyword, we also have the without keyword. As you could guess, this removes the record fields from the record. This is just the tip of the iceberg when it comes to records in Spiral. Here is a way of updating records that might seem familiar to those coming from F#, but has different, and we'd argue much better semantics. We call it the Lensic update. In F#, if you tried updating a nested record like this by accessing its subfields on the left side, what it would do is just update the topmost record, throwing away the rest. But in Spiral, it keeps the entire record around after the update is done. This makes it quite easy to immutably update a nested record. Let's compile it a few times so you can see what is going on. Nested tuples, nested records. It doesn't matter. In the compiled output, they will all get flattened to a single struct tuple, and with the compilation data provided to the various backends, we've made it so that it is easy to get the optimal representation in the compiled output. We are not done with records yet. Let us show you a feature that is unique to Spiral. Symbol types. You know how in other languages you can have an object and then access its methods and properties with a period followed by a name? Well, those names in Spiral can be bound to variables. Check it out. And once they are bound to variables, they can be used in various ways. For example, here, instead of having to give the record fields a static name, we can just insert a variable into them. And looking at the types in the tooltip, you can see that the record fields are all there. Nothing is preventing us from using the variable-bound symbols to apply the record. It is possible to do the same thing for modules. In the top-down segment, this isn't too big of a deal. You could try writing a function that takes in a symbol as an argument, but it would only accept a singleton type. But in the bottom-up segment of Spiral, things are completely different. In the real bottom-up segment of Spiral, the type inference is done in a bottom-up fashion. You don't get the editor support that you get in the top-down segment, and assigning types to objects such as arrays and functions becomes much more difficult. Closures and recursive functions also need to be given types ahead of time. Arguably, losing editor support and having to do the type inference by yourself are very big disadvantages, but in return, you do get a lot of power. And in the rare few % of the programming tasks where you actually need that power, Spiral has you covered. Many other languages have macros or metaprogramming systems, but Spiral is simply powerful. Putting in that real keyword is just a way of telling the type checker to go away. And we don't mean to say that no type checking is being done. Rather, the bottom-up type checking being done using the partial evaluator that underlies all of Spiral's functionality is the one that does the actual work of making it a static language. The top-down type inferencer is only an aid to help the programmer. You can think of it as how TypeScript acts on top of JavaScript. We'll go into more depth regarding the bottom-up segment of Spiral later. Right now, let's finish the record section by showing you what other special features exist for symbols. In the record updates, you can put them anywhere you want. You can put them on the right side of record with, you can also use them in record without. And in Lensic updates, you can also use the symbol variables on the left side of the with and without keywords. One minor thing we forgot to cover, you can in fact combine the with and without record updates. That should be it for records in this tutorial, but that is not all there is to them. In the core library, there are wrappers for map, left fold, and right fold operations over records. Anything you can do with immutable maps in F#, you can do with records in Spiral. Let's move on to unions next. Union types in Spiral are fairly similar to how they are in other functional programming languages. Here, we are demonstrating the most basic kind of union type, the non-recursive, non-generic one. It has the advantage of not needing heap allocation, and non-recursive union types are all that we'll have on the FPGA backend. But on backends that do allow heap allocation, we can make them recursive with no problem. To make an union type recursive, just add a rec at the end. Recursive union types have to be heap allocated, so you won't be able to use them on the FPGA backend. You'd just get an error during the code generation phase if you tried, but this is just to show that they exist. For both recursive and non-recursive union types, you can add generic parameters to them. Since we are using the C union case, the type inferencer is complaining that it cannot infer the type of the generic parameter. But if we pass in the D case with a fully inferred type, then it can infer the generic parameter automatically. If you want to destructure an union type, you should use a match statement. As mentioned, union type destructuring has to start with a capital letter. If you don't put in any arguments to the right side of it, unlike in F#, Spiral will assume that the variable is a wildcard. It has the full range of patterns for tuples, records, and unions, and you can mix them with the AND as well as OR patterns, much like you could in F#, so don't be afraid to try things out. We keep comparing Spiral to F# because that is the language it takes the most inspiration from and is the closest to syntactically. As you probably guessed by now, much like it and Python, Spiral is an indentation-sensitive language. With that out of the way, let's move on to more advanced topics regarding unions. We'll show you how you can unbox and create them in the bottom-up segment using just the key and the value. First, let us go over the nominal types. Nominal types are quite similar to single-case unions and are essentially the same thing as new types in Haskell. They are lightweight wrappers around other types, and unlike unions, don't have a runtime footprint. They have a use in that they can be used with nominal prototypes, which are Spiral's extensibility mechanism, and nominal prototypes are the same thing as Haskell's type classes. The reason why we are talking about them in the context of unions is that all unions have nominal wrappers around them by design. This design decision is so that raw union types don't spill into the user space, like they did in the 2018 version of Spiral. In the real segment, you can make use of some of the real core library methods to create them programmatically, without specifying an explicit constructor. With unbox, you can pass it the union type and a lambda, and it will automatically bind the key value pair to the first argument. And with nominal create, depending on the type you pass into it, it will either create an union or a nominal type. In this case, we will just rebuild the original union. These capabilities are really useful if you are working on serialization and deserialization functionality. The real core library has various other methods that would, for example, allow you to extract the union tags, and in the reverse, go from integer tags to the types for a particular union case, and this is very useful if you are serializing binary or one hotshot vector data. But that is beyond the scope of the current tutorial. If you are interested, there are examples of how this could be done on the Spiral repo, and maybe we'll cover serialization in a separate video. Next, we'll go over nominal prototypes. As mentioned, they are similar to Haskell's type classes, but unlike them, they have zero runtime footprint. They are always inlined due to them being propagated during the partial evaluation phase and aren't being passed around in dictionaries at runtime like in Haskell. You start off a nominal prototype with the prototype keyword, then you put in the name and the type variables followed by the function type. Type variables are just what would be the for-alls in a regular function, and in fact, that is how they are compiled. The type variables, apart from the first, can have any kind. The only rule is that they have to be used in the function type. We first have to define the nominals for which to create the instances, but with the nominals and their prototypes defined, we can then write out the prototype instances. When the nominals have extra type variables compared to the prototype definitions, those have to be added to the instance definition and written out explicitly. The compiler will give you an error if you forget them, so it is not a big deal. What you also need to write out are the prototype constraints on the instance type variables. And with that done, we should be good to go. The functionality of the nominal prototypes is intended for uses like generic printing, equality, and comparison, so the language needs them for that. A slight caveat is that in Spiral they cannot be defined on primitive types like integers, only nominals themselves. For that reason, the way you'd build a complete function for tasks like structural equality and comparison is by using a combination of nominals and compile time type matching. In the future, we'll probably be using them as initializers for neural net layers and fancy transformations of structures at compile time. But today's tutorial is just to introduce them. As you can see on the screen, we are done defining the instances and are moving to testing them out. If everything is fine, the nominals will print out something like int string string. We defined an operator function to chain them together. The rules for how the syntax for them works is the same as in F#. The dots inside the operators get ignored. They have the same precedence in the grammar as regular ones. If we apply the print prototype to them, we should get something along the lines of what we want. Here, Ghostlike is forgetting that interpolated strings in F# start with a $sign instead of F. F is how they start in Python. We are in the final stretch of this tutorial. Let us introduce layout types. Layout types were a lot fancier in the past version of Spiral, but in the V2 version that you are seeing in use now, they are quite easy to grasp. Remember how we said all the regular types are stack allocated in Spiral? If you want to heap allocate them, just apply one of the layout type wrappers around them. The are called heap and mutt. As you can see in the F# backend, they are allocated as regular heap records, and the mutable one has all the fields mutable. You can access them as you would a regular object, and for the mutable one, you can assign to its fields. You can also index into them through a nominal wrapper, but to our surprise, it doesn't seem you can assign to them that way. I guess that is something for a future version of Spiral. Note that you can index into them even if the fields are nested. And note how if you have nested records, they will get flattened inside the compiled output, much like they would be when returned from join points. That is one of the benefits of using Spiral. You can use complex data types without worry that their composition would increase the size footprint. We just need to mention, though, that since these are heap allocated, much like recursive unions and closures, we won't be able to use them in the FPGA backend. They are here just for completeness' sake. And that's a wrap with the basics of Spiral. In the next video, we will move on to the more advanced topic, something you'd never see in any other functional language. If you are interested, like and subscribe, and we will be out with the next video shortly. We think after we are done with explaining staging, we will have the foundation that we need to do some serious programming. The training wheels will come off, and we will demonstrate our true skill and power. We will show you what functional programming is really about. After this series, you will never think again that functional programming needs to be slow. That is just a side effect of how functional languages other than Spiral are built.